In this video, we're going to look at graphing variations of exponential functions. This is a good skill to have. Many models in engineering involve exponential functions, but with various transformations applied to them to match the situation that you're modeling. So for example, here let's take y equal to 2 to the x minus 3. So the exponential function is 2 to the x, and then I'm subtracting 3 after I've computed the value of 2 to the x. That order of operations is very important here. I first would find the value of 2 to the x, and then take the result and subtract 3 from it. So it seems like we should start with the graph of just the basic base 2 exponential function, which we're familiar with. There's y equal to 2 to the x. And remember, it has an x-intercept at x, or y-intercept rather, of at x equal to 0. The y-intercept is at 1. And then we have this horizontal asymptote here at y equal to 0, where it decays towards 0. So what I need to do is take each point on this curve and take the y value of it and subtract 3 from it. And that's going to shift that graph down rigidly by 3 units. So that y equal to 0, the horizontal asymptote, now gets moved down 3 units to minus 3. The curve is going to have exactly the same shape. And my y-intercept was 1, so when I subtract 3 from that, it will be minus 2 now. So that will be 0, minus 2, and there's the graph of 2 to the x minus 3. Okay, next let's look at y equal to 2 to the x minus 3. Now notice the order of operations is different here. I first subtract 3 from my input x, and then I use that as the input to the exponential function. So the order of operations is different from here as it was here. By subtracting 3 from the input, you're going to move the graph to the right 3 units. So this graph will be shifted 3 units to the right. The overall shape will be the same, but it's going to be moved over those 3 units. And in order to get some perspective of what's happened here, because it really doesn't look fundamentally different from what I just plugged in, or what I just plotted, let's plug in a couple of values to get that perspective of that shift to the right. So I'm going to take x to be 0, and we're going to find the new y-intercept. It's not going to be x or y equal to 1 anymore. I'm going to plug that in to 0 minus 3, so I'll get 2 to the minus 3, and then notice now it's 1/8. So that y-intercept is 0, 1/8. We're shifting to the right because when I plug in 0 to determine the point to plot on this one, I actually back up 3 units and grab the value 3 units to the left on this one, that smaller value of 1/8, but I end up plotting it at x equal to 0. So further to the right than what would have been plotted on the original graph. Let's do one more point. Let's take x to be 3, because if I take x to be 3, I'm asked to plot 2 to the 0 for the y-coordinate, and 2 to the 0 is 1. So that would have been the y-intercept at x equal to 0, but now it's moved over 3 units because that's what I have to plug in to get that y value of 1. So that now the y-intercept from before has moved 3 units over to now x equal to 3, y equal to 1. Okay, let's do another example. Let's take y equal to be 3 times 2 to the x. Order of operations, again, is critical in interpreting this expression. We do powers before we do multiplication. So the 2 to the x is computed first, and then I triple the result. First calculate the exponential function, and then triple the result. This will have the result of taking all the y values that we plot and tripling them. So it's going to stretch that graph vertically by a factor of 3. So everything's going to be scaled vertically by a factor of 3. The overall shape of the graph will look exactly the same as it did a moment ago. But when I take that value of 1 that y value for the intercept, and I scale it by a factor of 3, that now becomes 0, 3. This graph still changes by the same constant proportional amount as I go from one step to the next. I'll always be doubling, but now I'm starting with 3. So if I take x to be 1 and move over 1 unit, I'll have 3 times 2. I'll get 6. I will have doubled my 3, and now I'll be at 1, 6. If I was to go over to 2, I would double that and get 12. So this function here is very much the same as the original 2 to the x. I'm just starting with an initial amount of 3 on the y-axis there, and it's that 3 that's getting doubled each time. Let's look at one final example, and now we'll do something that involves space e. So here I want to graph y equal to 10 times e to the minus 2t. T is our variable. And then when I'm done computing that expression, I add 20 to the result. The first thing to observe is that there's a very basic exponential function involved, and it's this e to the minus 2t. We should probably start with an understanding of its graph and then apply various transformations to understand what happens to get my the graph that I'm looking for. So really what I'm taking is the number e to the minus 2, and I'm raising that to the tth power. So it's an exponential function, and the base of the exponential function is e to the minus 2. It's not a nice number, but I can get a feel for it. It's about 1 over 2.71. Remember, e is about 2.71, and then I'm squaring that. So it's somewhere between 1/4, that's 1 over 2 squared, and 1/9, that's 1 over 3 squared. But the bottom line is that this is some number that's less than 1. Somewhere between 1/4 and 1/9. Because it's less than 1, that tells me that it's going to be a decaying exponential function. Now, to continue analyzing our expression, it's important to follow the correct order of operations. I now know what e to the minus 2t will look like. It's some decaying exponential function, and then I'm scaling everything by a factor of 10. That's the next operation that I do. So if I'm looking at y equal to 10 times e to the minus 2t, I'm just going to take my original graph, and at t equal to 0 now, I'm going to see y equal to 10 times 1, or just 10. Again, e to the 0 will be 1, and so that factor in front is really telling you how much you have at t equal to 0. So our graph will be decaying, and initially, where it hits the y-axis, we'll see 0, 10. Finally, now the next operation is to add 20 to that result, and that will shift everything up 20 units. So if I plot the function I'm really interested in, I'm going to take the graph we just found and add everything, or add 20 to everything, lifting everything up. So the y-intercept now has moved up 20 units to 30. If I plug in 0 to this, I get 10 plus 20, which is 30. And my asymptote, which was y equal to 0 now, has moved up 20 units to y equal to 20. This gives you a really good perspective of what's happening here. We see some sort of decaying exponential expression, and its initial amount is 30, and it decays towards 20.